Hi everybody, and welcome to Chem Talk, where today we will be going over precipitation reactions and how net ionic equations factor into them, as well as discussing how net ionic equations are actually an important tool scientists use to protect the environment, as they are often used to depict neutralization reactions between acids and bases, and environmental scientists utilize this to neutralize bodies of water that have become acidic and harmful to fish. So let's get into it. We can begin with a few simple definitions. A precipitation reaction is a chemical reaction in which two dissolved, often ionic, compounds react, often via a double replacement reaction, to form one or more solid products, which are called precipitates. Net ionic equations themselves are chemical equations in which only the compounds or ions that are undergoing a chemical change or directly involved in the reaction are present. Those that are not are called spectator ions, which are ions that are present both before and after the reaction has taken place, and they play no role in the chemical reaction. When starting out, it's often a good idea to write out the complete equation of a precipitation reaction, and then identify the spectator ions and omit them from there. Let's try to form a net ionic equation with an example of a precipitation reaction. Here, I am going to write out the complete precipitation reaction for potassium chloride and silver nitrate. Seeing as the equation is already balanced, the next step is to separate each compound into ions with their charges visible. The next step is to eliminate the spectator ions. These are the ones present on both sides of the equation. In this case, these will be potassium and nitrate. Once we cross those out, we are left with this equation. And that's our net ionic equation. Net ionic equations can also be used to help determine if there is excess reactant and what the new concentrations of all the ions present in the reaction are. Let's say 50 milliliters of 0.5 molar potassium phosphate is mixed with 50 milliliters of 0.25 molar barium nitrate. Let's first write out the complete equation for this. Now let's separate them into ions, and let's assume it's aqueous if we don't say it's solid. We can see the spectator ions are potassium and nitrate, so we omit those to get the net ionic equation. Now let's use this equation to help us determine the limiting reactant. We have 50 milliliters of 0.5 molar potassium phosphate. So 0.05 liters of 0.5 moles per liter gives us 0.025 moles of potassium phosphate, which is 0.025 moles of the phosphate ion. And 50 milliliters of 0.25 molar barium nitrate. 0.05 liters times 0.25 moles per liter gives us 0.0125 moles of barium nitrate. This translates to 0.0125 moles of the barium ion. Now with 0.0125 moles of the barium ion times 1 mole of barium phosphate per every 3 moles of the barium ion, that will give us a yield of about 0.0042 moles of barium phosphate. Now with the phosphate ion, we have 0.025 moles of the phosphate ion times 1 mole of barium phosphate per every 2 moles of the phosphate ion. That gives us about 0.0125 moles of barium phosphate. Now 0.0042 moles is certainly less than 0.0125 moles, so we have barium nitrate as the limiting reactant. The next step is to find the new molarity of all the original ions in the reaction. It's important to keep in mind that the volume of the solution changes when mixing two liquids. We had 50 milliliters from each compound, giving us a new total volume of 100 milliliters, or 0.1 liters. Let's begin with the barium ion. This one is easy, because looking at the net ionic equation, we know the barium ion forms the solid barium phosphate, and the barium nitrate is the limiting reactant. This means all the barium ions will be consumed in the formation of the barium phosphate, so the molarity of the barium ions is 0. Now let's do the phosphate ion. We produced 0.0042 moles of barium phosphate. Now, 2 moles of the phosphate ion per every 1 mole of the barium phosphate gives us 0.0084 moles of the phosphate ion that was used up in the formation of the barium phosphate. We started with 0.025 moles of the phosphate ion. Molarity is the moles present over the volume, so we now have the starting amount of the phosphate ion, 0.025, minus the amount that was consumed in the production of barium phosphate, 0.0084, all divided by the new volume of 0.1 liters. So the new molarity of the phosphate ions is 0.166 molar. Let's do the nitrate ions now. This is a bit simpler because none of the nitrate ions were consumed during the reaction. This just means we have to divide the original moles of nitrate by the new volume. 0.0125 moles of the barium ion times 2 moles of nitrate per every 1 mole of barium gives us 0.025 moles of the nitrate ion. So we get 0.025 moles of the nitrate ion per 0.1 liters, giving us a molarity of 0.25 for the nitrate. And finally, we have the potassium ions. Again, knowing these were spectator ions helps us because all we have to do is divide the original moles of potassium by the new volume because we know none of the potassium turned into the solid barium phosphate. We had 0.025 moles of potassium phosphate, so that's 3 moles of the potassium ion per every 1 mole of the potassium phosphate, giving us 0.075 moles of the potassium ion. 0.075 over 0.1 liters gives us a molarity of 0.75 for the potassium. So we ended up with a solution that is 0 molar of barium ions, 0.166 molar for phosphate ions, 0.25 molar for nitrate ions, and 0.75 molar for the potassium ions. Something interesting to note about net ionic equations is how they can assist in real-life applications, like environmental chemistry and protecting the environment. It is where writing net ionics for acid-base neutralization reactions is helpful. Say you have a lake that some company has disposed of toxins in. Perhaps now there is an excess of hydrochloric acid in the lake, causing it to become acidic. In order to neutralize this, scientists can add a base that will produce a soluble salt and H2O when reacted with the hydrochloric acid. To ensure the salt is soluble, the net ionic equation of the reaction must result in only H2O being a product. Let's use sodium hydroxide to neutralize. This gives us a complete equation of HCl plus sodium hydroxide producing H2O and sodium chloride. Now, lucky us, this is already balanced, so all that's left is forming the net ionic equation and seeing if H2O is the only net product. So the spectator ions are sodium and chloride ions, and the net ionic equation becomes this, meaning the acid, HCl, becomes neutralized and the water is no longer acidic. To review, the steps to forming a net ionic equation are: 1. Write out the complete equation. 2. Balance the complete equation. 3. Write out the complete equation with aqueous compounds separated into ions. 4. Identify and remove spectator ions. And lastly, 5. Ensure everything is right by making sure the charges are balanced so the charge of the products matches the net charge of the ions. So that is all for today on net ionic equations and the stoichiometry involved with them. Thank you for tuning into ChemTalk. Make sure to visit our website www.chemistrytalk.org for hundreds of general, organic, and biochemistry articles.